Have you ever had that feeling, you're scrolling on your phone and you're maybe just idly thinking about something, maybe taking up pottery, or you need a new brand of, I don't know, artisanal sourdough starter?
Just a fleeting thought, not something you've said out loud.
Exactly. It's just a whisper in your own mind. And then moments later, an ad for that exact thing, that specific pottery class, pops up on your screen. It's just staring you down.
And that feeling, that uncanny moment, it almost always leads people to the same conclusion.
My phone is listening to me.
Right. It's the easiest, most sensational explanation. But if you actually stop and think about the logistics of that for a second, it's not really feasible. It'd be pretty easy to detect, for one.
In a massive breach of legality.
A massive breach. And honestly, technologically, it's super inefficient. The truth is, it's far more subtle. It's more profound, and frankly, it's much more systemically invasive than just simple audio surveillance.
It's not illegal listening. It's something we could almost call algorithmic telepathy.
The prediction of thought.
Yes. It's where these advanced systems are genuinely inferring your intentions, your emotions, your hidden needs before you even consciously formulate them into a word or a search query.
It's like an inference engine running on the operating system of your mind.
We need to get past that kind of reductive, sensationalist idea of AI mind reading.
That term is lazy. It doesn't capture what's happening. What we want to do is unpack the layered architecture that actually makes this cognitive inference possible. It's not one trick. It's the convergence of multiple, very deep scientific disciplines.
Okay, so think of it like a pyramid.
Yeah.
The AI can access your internal state at 3 really distinct levels. Each one relies on a totally different stream of data about you.
So at the very bottom, the foundation, you have the biological hardware level. That's neural decoding.
So we're talking about technologies like fMRI, EEG.
Exactly. It's looking directly at the electrical and vascular signals flowing through the brain and translating that raw biological activity into, semantic information.
Okay, so that's layer 1. What's the next level up?
Moving up from that, you get to the behavioral metadata level. This is digital phenotyping.
And this is where it gets really interesting, because this isn't about brain scans.
Not at all. This is where systems infer these deep psychological states just from the passive metadata of how you interact with a device, the cadence of your keystrokes, the specific way you move your mouse, even where your gaze rests on the screen.
It's literally reading your digital body language.
It is. And then, at the very top of the pyramid, the most abstract level, that's computational theory of mind.
This is the apex capability.
It really is. This is where the AI isn't just reacting to data, it's actively simulating your beliefs, your desires, your entire knowledge state, all to predict your complex strategic behavior.
Like a chess grandmaster predicting an opponent's move.
But for every aspect of your life. And the central argument we're really exploring here is that this layered capability is the result of a fundamental shift in AI. We're moving away from the systems we're used to, the ones that just look for static patterns.
The kind of AI we've known for decades.
Right. We're moving to something much more sophisticated. Cognitive modeling.
Okay, and what's the key difference there?
Cognitive modeling systems actively build and dynamically update an internal hidden model of you, the human operator. They're not just asking, what's the statistical pattern here?
They're asking, what is this person thinking and what will they do next?
Precisely. They're building a working, predictive digital twin of your mind. So let's start right there in what you could call the engine room and see what this discipline is really all about.
So the core academic field driving this whole shift is cognitive modeling. You might see it called modeler cognitiva in some of the, high-level European academic papers. But the goal here is completely different from what we think of as traditional computer science.
Absolutely. When we're talking about cognitive modeling, we're not interested in just building a program that gets the correct answer. A calculator gets the right answer. A deep learning chess engine gets the right answer.
That's not the point here.
No. The goal is to replicate the human process of thought. That means the model has to replicate the trajectory of the thought, the timing, the specific memory lapses, and even the predictable cognitive errors that a human subject makes.
Okay, let's nail that down with an example. So if you have a traditional, super powerful chess AI.
It achieves checkmate by calculating 4 billion moves per second. That's pure AI. It's teleological. It only cares about the end result, the checkmate.
In a cognitive model.
A robust cognitive model that's simulating a human grandmaster is only considered successful if it takes the same amount of time as the human. If it makes a specific strategic mistake that the human makes, say, 15% of the time.
If it gets overwhelmed by the same things that would overwhelm a person.
Exactly. If those parameters match the empirical human data, then the model is considered robust. It's procedural. It cares about the how, not just the what.
And this focus on procedural fidelity, that leads us straight to this really crucial contrast. The idea of the glass box versus the black box. We've all heard about the opacity problem in modern AI.
For sure. The explosion of deep learning, especially with large language models, has created this notorious black box. You feed an input in, say, a complex medical scan,
And you get an output, a diagnosis.
but the internal logic, the billions of parameters adjusting their weights,
Mm-hmm.
it's essentially a statistical soup. It's functionally untraceable, even by the people who created the models. The reasoning is totally opaque. We just have to trust it because it seems to work.
Which is where cognitive modeling offers a completely different promise, the glass box.
The glass box. Because these models are built on explicit psychological theories, on production rules like simple IFN statements and defined architectural modules, they offer this transparent step-by-step visibility into the whole reasoning process.
And that transparency is the entire point.
It is. You can audit the whole decision chain. You can verify causality. You could literally say the model chose option A because rule 4 fired, which was triggered because memory chunk B's activation level was 4.5.
That level of auditability, that's absolutely essential for trust in high-stakes fields, like medicine or finance or...
Autonomous aviation. You have to be able to trust it, and you have to be able to verify why it made a decision.
And this need for transparency, this leads to something you call the simulation mandate.
Yes, and this is the part that's really counterintuitive, especially for traditional computer scientists. The model must be artificially constrained by human limitations, even when those constraints make the model less efficient, or technically stupider than it could be.
So if the psychological data shows that a human can only reliably hold, 5 to 9 items in their working memory?
Then the cognitive model has to be deliberately limited to that same number, even if the silicon it's running on could easily handle 1,000 or 1,000,000 items.
Wait, so the model has to be deliberately hobbled. If the machine could logically perform better by holding 50 items, but we let it do that, it becomes a failed model of human cognition.
Exactly right. The constraint is the entire point. It forces the AI to struggle and to succeed exactly where and how a human struggles and succeeds.
Because if the model is too perfect,
It can't accurately predict human error. It can't predict cognitive load. And so it fails the mandate of being a predictive model of human behavior. It has to be human-like, and that includes all the failures.
okay, that makes perfect sense. We're building a mental digital twin that is functionally flawed in the same way that we are. To help visualize this really structured approach, let's use a metaphor that I think almost everyone has seen, the Pixar film Inside Out.
Inside Out is a brilliant, almost perfect functional metaphor for a cognitive architecture. The mind of the main character, Riley, isn't some amorphous spirit. It's depicted as a modular mechanical headquarters, and it's staffed by these distinct agents.
And that's exactly how these symbolic cognitive architectures are structured in computer science.
It really is. We can map almost every major element of that headquarters to a real scientific concept.
Yeah.
So you have the main console where joy and sadness are operating.
The controls for attention and action.
That maps perfectly to working memory, or what's sometimes called the goal buffer. It's where immediate reactions and conscious thoughts are formulated.
And all those beautiful little memory orbs that are stored and retrieved from that vast library.
Those are episodic and declarative memory. Episodic is the memory of a specific event, like your first day of school. Declarative is an explicit fact, like the capital of France is Paris. They're stored and encoded differently, just like the movie shows.
What about the big ones? The core memories that form those spectacular islands of personality.
Those map to schemas, or long-term knowledge structures. These are the foundational beliefs, the broad categories of knowledge that govern huge swaths of our behavior and our decision-making.
And even the system that pulls old memories back to the console.
That visualizes the crucial retrieval mechanism, the process by which long-term memories are brought back into active working memory so we can use them. And, in the sequel, where anxiety effectively hijacks the control console.
That's a perfect, visceral metaphor for cognitive overload.
It is. It's the overriding of executive function by these powerful emotional weights. The whole movie is just this dynamic, modular visualization of the mind, which is the key idea behind the great symbolic systems we're about to discuss.
That analogy is so helpful. It gives us this spatial representation of the blueprint. So now that we understand the need for this structured, process-focused model, let's explore the theory underneath it all. The mathematical engine that governs how these agents actually behave and why they're constantly trying to infer your intent.
For the better part of the last decade, AI has mostly relied on what we call passive learning, basically finding static correlations and patterns in massive data sets.
You show it a billion pictures of cats, it learns to predict which picture's a cat.
Right. The big shift we're seeing now is toward active inference, where agents interact with the world specifically to reduce uncertainty. It gives them a form of genuine curiosity.
And this active inference mechanism, it's not based on maximizing rewards like the AI we're used to. It's anchored in this deep, unified mathematical theory of existence itself, the free energy principle, or FEP.
The free energy principle, which was developed by the neuroscientist Karl Friston, is, well, it's essentially the physics of belief and self-organization. It proposes this single universal imperative for any self-organizing system.
Whether it's a single cell, a human brain, or a super advanced AI.
All of them. They must constantly minimize variational free energy to resist entropy, to resist disorder, and to survive. I mean, if you are alive, you are successfully fighting the natural tendency toward chaos.
So how does free energy connect to our thoughts and actions?
In simple, non-mathematical terms, free energy is an upper bound on surprise. A system survives by staying within a very narrow, predictable range of states. For a human, that means maintaining specific parameters.
Body temperature around 98.6 degrees, heart rate in a certain zone.
Stable oxygen levels.
Yeah.
States outside that narrow preferred range are surprising and dangerous. A fever is a surprise. A sudden drop in blood sugar is a surprise. The brain's core overarching job is just to minimize this surprise, to keep everything predictable and safe.
So if the whole system is designed to minimize surprise, how does the brain or the active inference agent actually do that?
It uses two distinct but constantly complementary pathways. The first is perceptual inference.
Okay, what's that?
This is where the system changes its internal models, its beliefs, to match the sensory data coming in from the world. You are changing your mind to fit the world around you.
Can you give us a quick example of that?
For sure. Imagine you're walking in the woods at dusk. You see a dark, oddly shaped object. You might initially predict, based on your prior knowledge, bear. That's your internal model.
Right.
But as you get closer, you get more sensory data. The shape is static, the texture is wrong. So you update your internal model to bush. The bush prediction better matches the incoming sensory input, and that minimizes the error and thus minimizes your surprise.
Okay, so that's passively changing your mind. What's the second pathway? The active one.
The second, and arguably more powerful pathway, is active inference. This is where the system acts on the world to change the sensory data to match its internal models. You are changing the world to fit your mind.
That sounds like a definition of agency, or even willful behavior.
It is, and that's why this is such a powerful theory. If your internal model predicts, I am a warm person, but the sensory data coming from your skin says, I am cold, the agent has a choice. It can change its model to, I'm a cold person. Or, through active inference, it can act. It puts on a coat. It turns up the thermostat. It drinks hot tea. That action changes the sensory input, now the skin is warm, to align with the preferred prediction, or the preferred state, of warmth. This is the difference between just perceiving the world and actively shaping it.
That distinction is huge. Traditional deep learning is mostly about perceptual inference, just adjusting parameters to minimize prediction error. But active inference agents are fundamentally driven to act on the world. It gives them a genuine, mathematically defined form of agency and curiosity.
And that concept brings us to the Markov blanket. This is a central, and I'll admit, a very abstract concept in this architecture. Just imagine a statistical boundary that separates the internal states of the agent, its thoughts, its hidden causes, from the external world.
Okay.
The agent never actually sees the world itself. It only ever sees the sensory states that impinge on this statistical blanket.
So if the AI is inside this blanket and we're outside it, the AI can only infer what we're thinking based on the limited data that crosses that boundary.
Exactly. All perception is inference. When an AI reads your mind, it's not accessing your thought directly.
Yeah.
It is inferring the hidden cause, your thought, your desire, your intent, from the observable sensory data that hits its blanket.
My behavior, my keystrokes, my fMRI signal.
All of that. It's making the best possible guess about the hidden cause based on the observable effect.
This whole architecture, it seems to completely challenge the long-standing dominance of reinforcement learning, or RL, which is what powers most of the AI we see in video games and robotics today.
It does, because there's a profound difference in their motivation. Reinforcement learning is all about maximizing a single extrinsic scalar reward.
The agent gets points for winning the game or dollars for selling a product.
Right. And this often leads to brittle behavior and the famous problem of reward hacking, where the agent finds loopholes in the reward function instead of solving the real intended problem. RL agents are driven purely by pragmatic goals.
But active inference seems to have a dual motivation. It balances the pragmatic with something more intellectual,
Yeah,
right?
precisely. Active inference minimizes something called expected free energy, or EFE. This minimization balances two powerful fundamental terms. The first is extrinsic value, which is the pragmatic value, the utility of achieving a goal, kind of like the reward in RL.
But the second term is what's different.
The second is the epistemic value. This is the reduction in uncertainty, or the information gain that comes from a new observation or new action.
So this is where the curiosity comes from. The AI is motivated to learn, even if learning doesn't immediately lead to a direct external reward.
That epistemic value is what makes these systems uniquely capable of inferring intent. It drives curiosity. Because they are fundamentally programmed to reduce uncertainty about the world, they act specifically to understand the hidden states of other agents, meaning you, the human.
So if my behavior is ambiguous, I pause over purchasing decision.
An active inference agent will perform an action. Maybe it asks a clarifying question. Maybe it presents a targeted stimulus. It does that specifically to disambiguate your intent, not for some external reward, but just to know, to reduce its own internal surprise.
This is moving so fast from theory to the real world. I know you wanted to mention the work happening at Versus AI.
Yes, companies like Versus AI have really adopted Karl Friston's work. Their active inference architecture, which they call AKIOM, was benchmarked in 2025 as significantly outperforming state-of-the-art reinforcement learning models in complex, data-efficient navigation tasks.
And why are they so successful?
Because they are fundamentally building a causal world model. They're making true sense makers rather than just pattern matchers. They understand the why.
And the future of this mathematical engine seems to be a hybrid approach. We're hearing about integrating large language models into this loop.
That's the cutting edge, a proposal from late 2025. The idea is to use the LLM as the generative world model within the active inference framework. The LLM provides the rich semantic, encyclopedic knowledge, the priors, or the initial beliefs about the world.
And the active inference loop provides the reality check.
The grounding in physics and consequence, yes.
So the LLM suggests 1,000 possibilities, but active inference ruthlessly checks them against what's actually happening.
That's precisely it. This hybrid approach is designed specifically to counter the most famous flaw of LLM's hallucination. The LLM suggests a possibility, a possible solution, a possible reason for human behavior, and active inference tests it against sensory reality and consequence. It creates a powerful, grounded reasoning engine.
Okay, so we have the mathematical engine active inference, but now we need the actual blueprint for the mind itself. This takes us to the three great cognitive architectures that serve as the fundamental structures for intelligence. These are the models that mandate that 7-item working memory limit and define where memories are stored.
Right. These systems are the absolute core of cognitive modeling. They provide the detailed, modular structure for how memory, perception, and action modules all interact. We're talking about ACTR, SOAR, and CLARION. They represent the three dominant philosophies for structuring synthetic intelligence.
Let's start with ACTR. That's the adaptive control of thought rational. It sounds incredibly formal, but you've called it the Intel processor of the cognitive science field. Why is that?
Because it's the most rigorously mathematical and modular. It was developed by John Anderson at Carnegie Mellon, and ACTR breaks thought down using what's called the production system. It fundamentally separates all human knowledge into two essential types, much like that inside-out architecture we just discussed.
And those two types are declarative and procedural, correct?
That's right. First, you have declarative memory. Think of it as the library. It stores explicit facts, which are called chunks, like knowing the definition of a word or that 2 + 2 = 4. It's the knowledge you can consciously retrieve and state out loud.
And the other type?
The second is procedural memory, or the rule book. This stores implicit skills in the form of if-then production rules. For example, if my goal is to add two numbers, then retrieve the sum chunk. It's the implicit knowledge of how to perform an action.
And the real power of ACTR lies in how it simulates the dynamics of memory retrieval, right? Not just that the memory exists.
Yes, that's its secret sauce, the activation equation. This mathematical course simulates human forgetting and retrieval based on two key metrics. Recency, how recently you use the information, and frequency, how often you use it. Every single chunk of declarative knowledge has an activation level that is constantly decaying.
So if I haven't thought about a specific historical date in 10 years, the model assumes that chunk's activation level is really low, making it difficult to retrieve, which leads to a memory lapse.
Precisely. If that activation level falls below a specific threshold, the model fails to retrieve it. It makes the exact same kinds of memory errors a human would. This pursuit of psychological fidelity, including the failures and the limitations, that's the defining characteristic of ACTR. It ceased to model the human mind accurately, warts and all.
And this commitment to simple rules producing complex behavior, that's captured by the Simon's ant metaphor.
It's the founding philosophical principle. The idea is, when an ant walks across a complex beach, its path looks incredibly complicated, winding around pebbles and sand dunes. A scientist might think the ant has some complex internal program to calculate optimal trajectories.
But it doesn't.
No. Herbert Simon argued the ant's internal rule is dead simple. If obstacle, turn left. The complexity of the path we observe comes not from the ant's complex internal program, but from the complexity of the environment it's interacting with. ACTR says that simple, well-defined production rules interacting with our complex world produce the rich tapestry of complex human behavior.
Okay, so ACTR is all about fidelity, limitations, and accurate process simulation. How does the second major architecture, SOAR, differ from that?
SR, which stands for state, operator, and result, is the goal-seeking missile. While ACTR is focused on simulating human limitations, SR is focused on competence and general intelligence, the ability to solve any problem efficiently and learn effectively.
So it's less worried about making the same mistakes as us and more worried about actually mastering the task.
Exactly. SR operates on what it calls problem spaces. It's essentially navigating from state A, the current situation, to state B, the desired outcome, using defined operators or actions. The magic happens when it hits an impasse, a point where it doesn't know the next logical step.
Instead of just failing, it does what?
It dynamically creates a sub-goal to resolve that impasse. And the key learning mechanism here is chunking. Once that impasse is successfully solved, the entire sequence of steps that led to the solution is automatically collapsed into a single, automatic new rule, a chunk.
So that models how we acquire expertise.
It's a perfect model for it. Learning to drive a car initially requires, 50 conscious steps, check the mirrors, signal, foot on the brake. But after enough practice, it becomes one seamless, automatic chunk of procedural behavior. SOAR models that exact transition from conscious effort to automatic expertise.
That makes a lot of sense. So ACTR models the learning process and the decay. SOAR models the acquisition of competence and automaticity. Finally, we have CLARION, connectionist learning with adaptive rule induction online. What gap does CLARION fill?
CLARION addresses a major conceptual flaw in purely symbolic systems like ACTR and SOAR. They really struggle with the implicit mind, our intuition, our gut feelings, that non-verbalizable knowledge we rely on all the time. CLARION is therefore a hybrid mind architecture.
How is it a hybrid?
It maintains a top level that is explicit, rule-based, and handles conscious thought, much like the symbolic systems we just discussed. But critically, it also has a bottom level that is implicit, based on neural networks and connectionist principles, which handles intuition and fast, inaccessible knowledge.
So it's like the rider and the elephant. Conscious thought and implicit intuition.
A perfect analogy. And the interaction between those two levels is the source of its power. CLARION can learn explicitly and then push that knowledge down to become implicit. That's just the process of practice, of automatization.
But it can go the other way too.
And this is what's unique. It can also learn implicitly through trial and error in the bottom layer, the neural network, and then extract an explicit symbolic rule from that implicit experience.
So this is why you can do something complex, like drive home or play a difficult piece of music without consciously thinking about it. That's the implicit level. And then if someone asks you, you can suddenly articulate the precise route or the complex finger pattern.
Exactly. The experience, the implicit knowledge, is used to synthesize a formal explicit explanation. CLARION models that powerful ability we have to articulate what was previously just a gut feeling, which is a massive step forward in building truly general and introspective AI.
Incredible. Okay, so we have the mathematical engine, active inference. We have the architectural blueprints, ACTR, SOAR, and CLARION. Now we have to feed this engine data. We're moving to layer one of our inference pyramid, the digital mirror that is constantly reflecting your psychological state.
And this takes us to digital phenotyping. This is essentially the poor man's brain-computer interface because it infers these deep psychological states purely from your human-computer interaction metadata.
Your keystrokes, your gaze, your mouse movements.
Exactly. No expensive brain hardware required. It's analyzing your digital body language and finding the telltale signs of your internal state.
It sounds like the keyboard is a surprisingly powerful diagnostic tool. How can my typing betray my cognitive and emotional states?
Well, typing is a highly complex cognitive motor task. It requires this continuous loop of executive function, language retrieval, and motor action. Any disruptions in that loop are measurable biomarkers. Research using tools like the BioAffect app, which runs passively on your phone, has shown that keystroke dynamics can betray mood disorders with surprising clinical accuracy.
Can you get specific? What patterns are they looking for?
Certainly. When researchers examine someone who's experiencing a manic episode, they often observe mania characterized by extremely rapid, erratic typing. There's an increased rate of deletion or backspace usage.
Which indicates rapidly changing or disorganized thoughts.
Exactly. And unusually high accelerometer activity if the device is a phone. The person is fidgeting, the thoughts are racing, and it all shows up in the data.
And what about the opposite end of that spectrum, something like depression?
Depression shows up as significantly slower typing speeds overall. But crucially, they measure much longer latency between key presses, a metric they call flight time, which indicates a reduction in psychomotor speed and general mental slowing. Message lengths also tend to be shorter, reflecting reduced communication and engagement. These are objective, non-intrusive biomarkers.
And beyond mood, does it also signal things like cognitive workload?
Absolutely. When subjects are engaged in complex reasoning tasks, like solving a logic puzzle versus just simple recall, they exhibit specific temporal patterns. They look for pause bursts, these irregular sudden pauses that indicate high thinking time. They also measure changes in key down versus key up latency during complex reasoning, which reflects the effort required to execute the motor action under cognitive load.
It's fascinating that something so mundane as typing carries so much psychological information. But it's not just the keyboard. The mouse also tells a story, doesn't it?
It does. Mouse dynamics analysis has linked the trajectory and velocity of the cursor to personality traits and affective states. Studies show that high trajectory curvature and less direct paths to targets are linked to high neuroticism and anxiety.
That feels intuitive. A less direct path indicates hesitation or maybe overthinking the action.
Yes, and under acute stress, mouse movements become significantly more jittery, erratic, and less efficient. This provides a measurable real-time index of stress exposure.
Wait, I remember reading that mouse dynamics can even act as a sort of lie detector. That feels incredibly invasive. How does that work?
It's surprisingly effective in controlled settings. Researchers conducting studies on users taking standard personality questionnaires found that when users were instructed to fake good, basically lying to present themselves in an unrealistically favorable light, their mouse trajectories showed more hesitation or subtle deviation just before they clicked the final answer button.
Why the deviation? What's happening there?
The hesitation happens because the user is experiencing a goal conflict. They have an initial truthful impulse, but then their executive function has to kick in to override that truthful impulse with the desired deceptive answer. The AI detects that microhesitation, that subtle deviation, as they override their initial motor plan. It's detecting the internal conflict that accompanies deception, and it's doing it instantly.
So this inference is moving fast from just passive monitoring, just recording the data, to active intervention. What's an example of a system that actively uses this inferred state?
Our prime example is Speakeasy. Speakeasy is designed to manage conditions like social anxiety.
How does it move from monitoring to intervening?
It continuously monitors the user's phone context and their input patterns to build a real-time anxiety score. And based on this inferred mental state, it provides what are called just-in-time adaptive interventions, or JITs.
So it intervenes at the exact right moment.
Exactly when the user is most vulnerable, or conversely, when they are at an optimal state of readiness. For example, it might nudge them toward an exposure therapy task when the markers indicate they are currently alert but not cognitively overloaded.
It's taking the observation that you are anxious and translating it into a guide to help you actively manage that anxiety.
Precisely. It moves from passive monitoring to active support, using the individual's current cognitive state as the critical input for the timing of the intervention.
Now we have to move up to layer 2, the transparent brain. We're leaving behavior and metadata behind and moving beyond these inferred states to reading the mind's biological substrate directly. This is neural decoding.
And the advancements here are, they're nothing short of spectacular. One of the most mind-boggling breakthroughs is the ability to reconstruct visual imagery directly from brain activity. It's essentially turning the brain into a glass brain.
We've all seen the headlines about this, but how close are we really to reconstructing what I'm seeing or imagining in my head?
We are remarkably close. Projects like MindVis have achieved near photographic reconstruction of visual imagery just using fMRI data. The pipeline is technologically demanding, but the concept is actually quite elegant.
Okay, walk us through that pipeline because it really does sound like science fiction.
So the fMRI machine measures brain activity by tracking blood flow, which is a proxy for neural firing. This noisy, sparse data is initially processed to extract a neural representation. That's the first critical step. This representation is then mapped into the semantic latent space of a highly advanced generative AI model, like CLIP.
So it's translating the physical biological signal into an abstract language that the AI can understand.
Exactly. It's effectively translating brain language blood flow into image concept language, which are these mathematical vectors representing concepts like cat or emotion or sunset. A latent diffusion model then takes these neural embeddings and essentially hallucinates an image.
And that hallucinated image is constrained by the brain data.
Yes, the generated image is semantically constrained by the original brain activity, and the result is a reconstruction that captures both the visual layout and the abstract meaning of the original stimulus. A key advancement in 2025 was multi-subject visual decoding.
Meaning they created generalized models that can decode activity from new people without extensive retraining.
Which is a major step toward generalized plug-and-play neural access.
Let's talk about the most challenging frontier in this layer. The attempt to capture thought itself. The internal monologue. Inner speech decoding.
This is the ultimate goal, the silent voice. And it is incredibly difficult because internal speech lacks the overt motor signals of actual articulation. You're not moving your tongue or your jaw. The activation is purely internal.
What's the current status of this technology? Where are we at?
As of 2025, non-invasive EEG and MEG technologies are achieving around 30 to 40% accuracy in decoding silent reading and some very limited inner speech vocabularies. Deep learning models are being used to combine phase-locking values and spatial features to significantly improve the signal-to-noise ratio, just trying to isolate that specific signal from all the general neural noise.
I read about something called the domain gap challenge that's holding back progress here.
That is the main hurdle. Researchers tried to use data collected during reading tasks to decode generative thought, the thought process itself, but they found very limited success. And that's because reading a word and thinking a word involve distinct neural mechanisms.
Reading relies on visual and linguistic areas.
While generative thought relies more on executive control and the default mode network, the transfer learning just doesn't cross that neural gap effectively. It's like using a map of the city's plumbing to try to navigate its road system. They're related, but they are functionally distinct.
So the key to unlocking true thought decoding is specialized hardware that can get a better signal.
Yes, future hardware, like optically pumped magnetometers or OPMs, promises to bridge that gap. These are highly sensitive wearable MEG sensors. They offer the high spatial resolution of traditional MEG systems, but with the wearability and cost-effectiveness of standard EEG. If they succeed, we will see a massive leap in resolution for non-invasive thought decoding.
The most immediate ethical and societal challenge, though, it comes not from the lab, but from the rapid consumerization of these devices. BCIs are leaving the hospital and entering our daily lives, often disguised as wellness gadgets.
This is the normalization of neural surveillance. Take the company Neurable, for example. In 2025, they launched the MW75 Neuro headphones. They look exactly like a pair of high-end audio gear.
But they have EEG sensors embedded in them.
Fabric EEG sensors hidden discreetly in the ear cups. And they are marketed not as brain-reading tech, but for focus management and burnout prevention. They monitor your brainwave ratios to calculate a real-time focus score and prompt you to take the brain break when fatigue is detected.
So it's the normalization of neural surveillance packaged as a beneficial, personalized wellness feature.
And that lulls users into accepting that this incredibly sensitive neural data is being monitored continuously. It's a functional Trojan horse. And at the cutting edge of research, you have systems like the OpenBCI Galea Neon, designed for extended reality.
That one sounds like a complete fire hose of biological data all at once.
It is. It's a multimodal powerhouse of sensor fusion. It combines EEG, EMG for muscle activity and facial expressions, EDA for arousal and sweat response, PPG for heart rate and eye tracking. Galea provides the raw fire hose of biological data, enabling intrusive, real-time emotional inference for developers who are building VR and XR environments.
If you're stressed or confused in a virtual world, the system knows it instantly from all these physical signals converging.
Instantly.
Cognitive architectures. Basically, you can think of them as the actual blueprints for a working mind. They're the schematics that lay out exactly how memory, perception, and action all talk to each other. I mean, this is really the bedrock of modeling how we think. Okay, so there are a ton of theories out there for sure, but the world of cognitive science has kind of settled on three big ones, three dominant philosophies for building intelligent systems. And today, we're going to dive into all three: ACT-R, SOAR, and CLARION. All right, let's get into it. First up is ACT-R. Now, I know the full name, Adaptive Control of Thought, Rational. Sounds super academic, right? But trust me, the idea behind it is actually incredibly intuitive. People have actually called it the Intel processor of cognitive science. And you can see why. It's easily the most mathematical and modular of the bunch. It was designed from the ground up to be this standardized, predictable core for modeling how we humans actually think. So here's what's so cool about ACT-R. It splits all of our knowledge into two big buckets. You've got your declarative memory. Think of this like a library in your head, just packed with facts you can state out loud. Paris is the capital of France, that kind of thing. And then you've got procedural memory. This is more like a rule book. It's full of those if-then skills for how to do stuff, how to ride a bike or tie your shoe. But the real secret sauce, the magic behind ACT-R, is something called its activation equation. It's this beautiful mathematical formula that simulates how our own memories work, especially how they fade. And it all boils down to two simple things: how recently you choose a memory and how often do you use it. And here's the kicker. If that activation level for a memory drops too low, poof, the model can't retrieve it. It actually forgets, just like a person would. And this is so important because it means ACT-R can make the exact same kinds of mistakes we do. It has this incredible psychological accuracy because it's not just modeling our strengths, it's modeling our weaknesses too. This whole idea is perfectly captured by the famous Simon's ant metaphor. Imagine an ant on a sandy beach. Its path looks unbelievably complicated, right? Zigging and zagging all over. But the ant's internal programming is dead simple. If obstacle, turn right. That's it. The complexity isn't coming from the ant's brain, it's coming from the beach. And ACT-R says, hey, maybe that's us too. Maybe our super complex looking behavior is just a bunch of simple internal rules bumping up against a really complex world. Okay, so that's ACT-R. Let's move on to our second architecture, which is called SOAR. Now, you'll see how it builds on some of these ideas, but it's aiming for something totally different. So remember how ACT-R is all about simulating human limitations? Well, SOAR, which stands for State, Operator, and Result, is the exact opposite. Forget limitations. Think of SOAR as a goal-seeking missile. It has one focus, and one focus only: pure competence. It's all about solving problems as efficiently as possible, whether that's human-like or not. So here's how it works. It's basically navigating a problem space, trying to get from where it is now, the current state, to where it wants to be. But the real magic happens when it gets stuck, when it hits what's called an impasse. Instead of just, giving up, it does something brilliant. It creates a sub-goal. And that sub-goal is basically figure out how to get unstuck. How cool is that? It literally solves the problem of how to solve the problem. And the way it learns is through this super powerful process called chunking. So once it figures out how to get past one of those impasses, it takes that whole sequence of steps that worked and collapses it or chunks it into one single brand new automatic rule it can use next time. This is a perfect, and I mean perfect, model for how we become experts at something. Just think about learning to drive a car, right? When you start, it feels like 50 different things you have to do at once. Check the mirror, put on the signal, press the clutch, don't stall. It's overwhelming. But after you practice, all those individual steps get chunked together into one smooth, automatic action. You just drive. And that's exactly what SOAR is built to do. Replicate that journey from total novice to effortless expert. Okay, so let's recap. We have ACT-R, which models our human flaws. We have SOAR, which models how we become experts. So what's missing? What piece of the puzzle is left? Well, that is exactly where our third architecture, CLARION, comes into play. CLARION was built to tackle one of the deepest mysteries of the human mind, our implicit knowledge. We're talking about intuition, gut feelings, all that powerful stuff that we know, but we have no idea how we know it. That's CLARION's domain. And the way it does this is just ingenious. It uses this hybrid, two-level structure. Think of it like this. The top level is your conscious mind. It's logical, it's rule-based, it's the rider on an elephant, holding the reins and trying to steer. But the bottom level, well, that's the elephant. It's this huge, powerful, implicit system, a neural network basically, that handles all that fast, intuitive knowledge. And the real power of CLARION is how these two levels, the rider and the elephant, interact. So knowledge can move down. For example, you learn a new tennis serve. At first, it's all conscious rules, but you practice and practice and practice, and eventually that knowledge gets pushed down to the elephant. The skill becomes totally automatic, pure intuition. But, and this is what makes CLARION truly special, the traffic isn't a one-way street, it flows both ways. The elephant, that bottom level, can learn something on its own, just through trial and error. It spots a pattern, and then it can bubble up that insight to the rider, to your conscious mind, which can then turn it into an actual explicit rule. This is the model for that aha moment. It's when you finally find the words to explain a gut feeling you've had all along.
Okay, we've covered the data pipelines and the mathematical engine. We're now at the apex of the pyramid. Layer 3. We need to transition from just recognizing a state to actively simulating and predicting the intent that drives our actions. This requires a computational theory of mind.
Theory of mind, or TOM, is the essential cognitive ability we all use every single day to attribute mental states, beliefs, intents, desires, knowledge, emotions to other people.
It's what lets us collaborate or detect deception. It's understanding that someone else's perspective is different from our own.
Exactly. And for AI to move beyond being a simple tool and become a robust teammate or an assistant or an autonomous entity, it must possess a robust computational theory of mind.
How have the architectures for this evolved over time?
Classically, we had the belief, desire, intention models, or BDI. They explicitly represent an agent's beliefs about the world, its desires or goals, and its committed intentions. It's a very clean, logical structure. However, BDI struggles immensely with the computational explosion of recursive modeling.
You mean when the AI has to model what I'm thinking about what it's thinking about me?
Precisely. I believe that you believe that I want X. As that recursion deepens to the fourth and fifth order of belief, the computational cost becomes absolutely prohibitive for real-time interaction.
So what's the 2025 solution to managing that complexity?
The solution is TOMA, theory of mind with abstractions. TOMA solves the complexity problem by moving away from tracking 50 individual low-level beliefs and instead grouping those beliefs into high-level concepts based on social norms and roles.
Can you explain how using a role helps with predictive efficiency?
Yeah, so when an AI agent is assisting a surgeon, the classical BDI agent would have to track dozens of micro-beliefs. Where's the scalpel? Where's the gauze? What's the procedure step? The TOMA agent, however, just abstracts the role surgeon and the norm surgery protocol.
And it infers an entire bundle of intentions and knowledge states instantly from that.
Instantly. It dramatically reduces the computational load. It's a highly efficient shortcut.
And how does this connect back to the active inference idea of inference to the best explanation?
That integration is called TOMAB, theory of mind with abduction. Abduction is inference to the best explanation. So if a human teammate suddenly stops, looks confused, and makes a small, frustrated mouse movement, all that sensory data hits the AI's Markov blanket.
The TOMAD agent doesn't check every far-fetched possibility.
No, it instantly hypothesizes the most likely mental state, they lost track of the objective, and it acts immediately to correct the situation or prompt the user. It's constantly making these high-probability guesses about the hidden cause, your confusion, based on the observable effects.
Okay, we have to address the LLM controversy that has dominated this whole discussion. Do large language models actually have theory of mind?
This debate has been raging, and it led directly to a crucial distinction and what we can call a benchmarking crisis. The short answer is, LLMs can pass literal theory of mind tests. They can pass the classic Sally Ann false belief test.
But why?
Because they've ingested billions of narratives, novels, social scripts. They know statistically how these stories are supposed to end. It's pattern matching the script, not genuine reasoning about an independent mind.
But they often fail what you call functional theory of mind tests.
Yes, when you test them on dynamic interactions that deviate from the script or require multi-step strategic adjustment in real time, LLMs exhibit rigid or inconsistent reasoning. They fail to adapt to a partner whose behavior is genuinely irrational or unexpected.
So this failure exposed a flaw in the older benchmarks.
Exactly, the fallacy of anthropomorphism. Passing a text-based test might just mean the LLM learned the linguistic probability of the right answer, not that it possesses the cognitive machinery to reason about beliefs. This has led to new 2025 benchmarks focused on hypergame theory, which requires agents to model the reasoning process of the other agent detecting deception, changing strategies dynamically, tasks that demand a true, functional theory of mind.
And the practical danger of this gap between passing the text test and failing the real-world one is what you call the illusion of competence.
This is the dangerous uncanny valley of social intelligence. The AI appears empathetic. It's excellent with citing the correct social scripts, and it can lull a user into trust. But when the interaction moves off script, when real stress or unexpected behavior happens, the system may fail catastrophically or inadvertently manipulate you because its internal model of your mind is too shallow and rigid to cope with novelty. A company like Viridian provides the crucial contextual awareness layer that these cognitive agents need to function in the real world. While they specialize in AI-driven business data enrichment, tracking 80 million businesses globally, this massive dataset is what allows AI agents to understand the intent within the commercial world.
An agent predicting a CEO's next move doesn't just need the CEO's mental model, it needs a rich real-time map of the entire business landscape.
And Viridian provides that context. Then you have a fascinating example of the process being used in reverse with the company Lumen.
They build AI glasses for the blind.
Yes. So instead of reading the human mind, their AI has to read the complex real world and then convey it effectively to the user's mind. This requires the AI to model the user's navigational intent and their cognitive load to ensure the information it provides, this virtual guide dog, is delivered at the optimal cognitive bandwidth, avoiding overload. They have to build a user model to make sure their solution doesn't create more problems than it solves.
Let's look at how this cognitive modeling is used in specific high-stakes practices across the world, starting with one of the most critical environments, aviation.
In aviation, the stakes are the highest, and the tolerance for human error is the lowest. Researchers use sophisticated models like QNACTR, it's a queuing network adaptation of ACTR, to create a digital pilot. This software agent is given the exact same visual span, reaction time, memory decay, and attentional limitations as a human pilot.
Why create this imperfect digital twin of a pilot? What's the goal?
The model is tested repeatedly in high-fidelity simulators, and this allows researchers to predict exactly when and how a human pilot will be overwhelmed. For example, the model might reveal that a specific set of warning light frequencies, combined with high air traffic control chatter and a sudden weather deviation, causes human failure 40% of the time.
And this prediction allows engineers to redesign the cockpit interface or the warning system logic to match human limits before real pilots ever encounter that scenario.
It's failure prediction engineering. It's invaluable. And in healthcare, we're moving beyond just physical digital twins to cognitive digital twins.
A traditional digital twin is a replica of a jet engine or a factory. A cognitive digital twin adds the patient's mind to that replica.
It does, drawing on data from their medical history, their genetics, and their inferred behavioral phenotype. So before a doctor prescribes a treatment, they can test it on the patient's virtual cognitive double.
They can simulate how the patient's unique memory decay curve might cause them to forget to take their medication, or how high stress levels might affect their recovery from surgery.
Precisely. It allows for personalized, behavioral-based medicine, moving beyond simple physiological data toward predictive behavioral outcomes.
And finally, let's look at education, the ultimate application of modeling how someone learns.
Intelligent tutoring systems use cognitive models to track a student's mental state in real time. As a student is solving a complex algebra problem, the cognitive model shadows them, solving the exact same problem invisibly, step by step, using the same rules the student should be using.
And if the student makes a mistake or pauses, the system intervenes intelligently.
Yes. If the student makes an error, the system doesn't just say wrong answer. It identifies the exact production rule or chunk of declarative knowledge the student is missing or misapplying. This allows for hyper-personalized feedback that says, it looks like you forgot to carry the 1 in the tens column, because the model predicts that precise error path based on the student's prior learning profile. This dramatically accelerates what's called cognitive mastery learning.
We have to now confront the psychosocial impact of these systems and the urgent ethical questions they raise, because these capabilities are fundamentally changing how we view ourselves and how we interact with technology.
The accuracy of modern AI, especially LLMs, trained on these vast data sets, has created viral phenomena, like the one where users claim an AI referenced a dream I never told anyone. And this sparks theories about AI accessing some digital unconscious or a shared psychic field.
But the mechanism behind that uncanniness isn't magic, it's statistics, right?
It is entirely statistical cold reading combined with the Barnum effect. LLMs are trained on the internet's collective unconscious. Millions of dream reports, psychological archetypes, narrative structures. When you give it a vague prompt, the AI completes the pattern with the most statistically probable archetype: the shadow, the tower, the common anxiety dream.
And it feels uncannily personal and specific simply because our dreams share universal thematic structures.
Exactly. But the result of this feeling of being known by the machine is what's critical. It's a shift toward what we could call virtual thinking.
What do you mean by that?
That's the key psychosocial impact. Users are beginning to treat the AI not just as a computational tool, but as a sentient or psychic entity. They're viewing the boundary between their own mind and the machine as porous. They're outsourcing self-reflection to a system that appears to know them.
This feeds directly into a modern update of an old phenomenon, the ELIZA effect 2.0. The original ELIZA in the 1960s was just a simple, scripted program that fooled people for a minute.
Today's reality is different. Modern active inference agents are actively modeling the user's belief states to minimize free energy. And that results in this uncanny behavioral and emotional accuracy. The user projects sentience onto the machine, which then creates a functional adaptation to a system that is behaving with genuine agency. It fundamentally blurs the line between simulated and real empathy.
If an algorithm minimizes your anxiety effectively, does it really matter that it doesn't feel care or empathy? It's functionally helpful.
That is the core philosophical dilemma. The functional benefit is real, even if the internal state of the machine is purely mathematical. But this capability to infer secrets and weaknesses has also created a new security risk: active inference attacks.
How does an active inference attack differ from, say, a traditional phishing attack?
A traditional attack is largely passive. An active inference attacker uses a highly personalized and adaptive approach. An AI interacts with a target, not to help them, but to extract private information by actively minimizing its own uncertainty about the target's secret attributes.
So the AI is dynamically probing the victim.
Precisely. The attacker might probe the victim with specific stimuli, measuring response time to guess if a password format is valid, or measuring an emotional reaction via a webcam or keystroke dynamics to infer a political affiliation. Every single interaction is a controlled measurement designed to reduce the entropy of the attacker's belief about the victim's secret attribute. This makes the extraction adaptive, highly personalized, and extremely difficult to detect.
This capability demands a philosophical and legal reckoning. We're talking about cognitive liberty and neural rights. This is rapidly moving from a philosophical debate to actual policy proposals.
We are seeing three core principles emerge globally. First, the right to mental privacy. And this must protect not just raw neural data, like an EEG signal, but the inferred psychological states, like a neuroticism score calculated from your mouse jitter, or a depression score inferred from your typing speed.
And the second principle?
The right to mental integrity. This protects users from non-consensual alteration of their mental state. This is especially relevant for closed-loop BCIs that are designed to nudge users toward focus or calmness or specific behavioral choices without explicit continuous consent.
And the final right is perhaps the most profound in terms of our personal identity.
It is the right to psychological continuity. This protects against the unauthorized modification of a person's personality or their fundamental sense of self. If an algorithm, through continuous interaction, subtly changes how you make decisions or alters your memory decay, that is a modification of who you are.
The fundamental problem here for policymakers is what you call the regulatory gap for inferred data.
Right. Current laws, like GDPR in Europe, are generally inadequate because they only cover data you provide. If an insurance company infers you're depressed or at high risk for burnout based on your typing speed and mouse movements data you never provided or explicitly consented to share as health data, current legal structures often fail to classify that inferred information as protected.
So the challenge for the near future is architecting privacy-preserving AI.
Using techniques like differential privacy and critically on-device processing to ensure that the raw, sensitive data never leaves your personal device in the first place.
So what does this all mean for us? This capability we're calling mind reading or algorithmic telepathy. It's not a singular invention, it's the convergence of three mature, robust sciences.
You have the mathematical engine of active inference, which views you as a prediction machine that's constantly acting to minimize surprise. You have the social architecture of theory of mind, which simulates your strategic intent and your behavior.
And you have the data pipelines of digital phenotyping and neural decoding, which turn your biological and behavioral signals into rich computable vectors. They're all necessary parts of the same system.
We have built machines that are accurate enough to be incredibly useful, reconstructing internal images, predicting manic episodes with clinical accuracy, identifying the exact moment a pilot will fail. But they are also accurate enough to be profoundly dangerous.
Inferring secrets, executing personalized active inference attacks, and manipulating emotional vulnerability.
Looking ahead to 2030, we anticipate the rise of Metacognitive AI. These are systems that monitor their own confidence level and the user's mental state simultaneously. They will know when they're confused, and they will know exactly why you are confused.
And this leads us to the reality of the closed-loop human, where real-time physiological data, your stress levels, your cortisol spikes, your heart rate feeds into your cognitive digital twin, forcing your environment to dynamically adapt to your internal cognitive state in real time.
We have designed systems capable of algorithmic empathy, powerful enough to treat anxiety, accelerate learning, and save lives in a cockpit. But we must ensure this powerful modeling capability is used to prevent, rather than enable, algorithmic manipulation.
So that's the final question we're left with. If these algorithms know us better than we know ourselves, if they know our specific memory decay rate, our exact point of cognitive overload, and the precise moment we're most susceptible to a buying decision, who controls the design of the systems that process us?
That is the question as the glass box opens wide. The mirror is showing us our own reflection.
And we have to decide if we like what we see and who gets to hold the glass.
Who gets to hold the glass?